Thanks for joining me for the beginning of Chapter 3 on multivariable functions and partial derivatives. In this video, we are going to begin to explore functions of several variables, section 3.1. So the goal of this section is to become familiar with functions of several variables, including their notation, domain and range, and their means of representation. So definition 3.1.1, a function of several variables, or a multivariable function. F is a rule that assigns to each ordered list of numbers to a point x1, x2, xn in Rn at most one real number y. Notation, in general, we write f goes from Rn to R, and y is f of x1, x2, xn. In the case when n equals 2, we write f goes from R2 to R, and typically we would write z is f of xy instead of using subscripts. And when n equals 3, we write f goes from R3 to R, and very typically w is f of x, y, and z. So let's look at example 3.3.1. Suppose that f of x, y, and z is equal to 2x minus 3y over z squared, and we're asked to calculate w, which is f of 1, 3, 1/2. So this works exactly as you would expect it to. The values are given in order, so x is 1, y is 3, and z is 1/2. So w, which is f of 1, 3, 1/2, is 2 times 1, you just plug in the values, 3 times 3 over 1/2 squared, which gives us 2 minus 9 times 4, 2 minus 36, or minus 34. Domain and range. Definition 3.1.2. The domain of a function f of x1, x2, up to xn is the set of points in Rn on which the function is defined, and the range of f is the set of values in R that the function can take. So let's go and do example 3.1.2. We're asked to find the domains of the following functions. We're then asked to sketch the domains either in the plane or in space as appropriate, and to describe the set in words. So if we look here at part A, f of xy is the ln of y minus x squared. So that's a real valued function, which, as you remember from your calculus course or your course on functions, can only take non or positive values, not 0 either. So y minus x squared must be greater than 0. Y, therefore, has to be greater than x squared. That is describing to us a region in the plane. So if we're going to try and sketch this and graph it, we're going to want to graph the boundary first. And the boundary is going to be the parabola. Y is equal to x squared. But we need to be careful. We need to be careful because we are not equal to. We are greater than, but not equal to. So we're going to graph that boundary as a dotted line to show that it is not included. Y is equal to x squared. Now, y is greater than x squared. We're going to have the part that is above that parabola, so we'll shade in that region. But if ever you are not sure, is it the part that's above, is it below? If you're not sure what region to shade, you can just pick a point. For example, if I pick the point here 1, 0, 1 is greater than 0, so that is clearly in the region, as opposed to if I picked a point out here, minus 1, 0, well, minus 1 is not greater than 0, so that is the incorrect region. So you can always just pick a point to figure out where you need to shade. Now, we've graphed this in the plane in R2, but really this is the domain of a function in three-dimensional space. So if I wanted to just give you an idea of how this would look in three-dimensional space, we're talking about the graph of y is equal to x squared, which I could embed in the x, y plane. This is the x-axis and the y-axis. And if I were going to shade it, right, it would of course just be here. So what is that telling us? The function graph would be above or below this parabola shaded region in the xy plane. And we'll go take a look at that right now. Let's go and take a look at the graph of f of xy is the ln of y minus x squared, and we'll see exactly that this shaded area is the shadow of the graph onto the xy plane. Here's the graph of the ln of y minus x squared. It's looking rather ragged down the side because those values are going down to minus infinity, and the grapher is not able to numerically deal with those particularly well. But you can see that it has a nice, well-defined shape over a certain region of the xy plane only. And the region of the xy plane, you may not be surprised to learn that it's exactly what we shaded in. It is the parabola, y is equal to x squared. Now that boundary, of course, is not included. You can see the function is looking very ragged as we go down there because that boundary is not included, and the grapher is having a little bit of trouble, as I say, as those values go down towards minus infinity. But that is the idea when you're finding the graph of or the domain of a function in two variables, is that you're finding the projection, the area over the xy plane in which the graph sits. Okay, let's look at part B. G of xy is 1 over x squared plus y squared. So the same rules apply as always apply in function calculations. There are elements, there are operations that you are not allowed to do, and we're not allowed to divide by 0. So x squared plus y squared cannot equal 0, which means that x and y cannot be 0 at the same time. And one way to write that is to say xy cannot be 0, 0. So we wanted to describe, I forgot, it said describe the set in words. So if I go back to part A, describe the set in words, this is the region above the parabola y is equal to x squared and not including the boundary. So back to part B. I would say that this is all of R2 except the origin, except the point 0, 0. That's our domain. So if we want to graph that in the plane, how would you graph all of R2 except the origin? Well, one way of doing it is to graph the origin as an open circle not included, and you graph and you shade in the rest of the plane around it. Lastly, let's go and take a look here at h. The square root needs fixing. H of x, y, and z. This time we've got a function of 3 variables. It's the square root, so what's under the square root still has to be positive or 0. So 4 minus x squared minus y squared minus z squared has to be greater than or equal to 0. Rearranging this, and that's x squared plus y squared plus z squared has to be less than or equal to 4. So if we were to go and graph the boundary where x squared plus y squared plus z squared equals 4, that's something that we have seen recently. That is the equation of a quadric surface, and in particular, a sphere. So if we go and graph this sphere is the boundary. We have everything that is in the sphere, on the boundary, and the interior. So in 3 dimensions, it's harder to graph whether you're including the interior or not, so we really, giving it in words can be very useful. So we have the boundary and the interior. So the boundary and the interior of the sphere of radius 2, centered at the origin, which means that these are intercepts of 2. Lastly, let's just have a quick look at what a table of values looks like for functions, and we'll do graphical representations in another video. So in the case of a function of two variables, it's fairly easy to represent the function by a two-dimensional table of values. Right? So we have the x values, the y values, and then the z, the function values inside the table. So we're asked in example 3.1.3 to use the table of values to find f of 2, 1, f of 1, 3, and to find all points where z is equal to 3. So f of 2, 1. F of 2, 1, we are literally just reading this from the table. The x value is 2, the y value is 1. That gives us f of 2, 1 is 10. F of 1, 3, f of 1, 3. So the x value is 1, the y value is 3, f of 1, 3 is 4. And lastly, we want to find all places where z is 3. So where does the function take the value 3? Well, we can see 1, 2 of them. So the first one is at the point 0, 1. Right? The first one, 0, 1, is this 3 here. So at the point 0, 1. And the second one is here. And that is at the point 3, 2. So at 0, 1 and at 3, 2. In the next video, we'll go and look at different ways of representing a function of several variables graphically.